Okay, so here we have a problem considering the general one-dimension heat conduction equation. So, heat conduction equation, and we'll go ahead and identify some elements of this equation. So this is the temporal change. This element here is the diffusion of temperature. Just write temp. And this is heat generation. Okay. So we're assuming that it's steady state heat transfer conduction with constant heat generation. How do you simplify the previous equation? So what do these words here actually mean? So steady state means that your temporal change is equal to 0. So that's equal to 0. And constant heat generation just means that your Q dot is not equal to 0. So it is present. That means that this term, or the heat conduction equation, simplifies down to this right here. Change that. Equal to. So just a little proof to show that what we're going to do next is valid. Just a little visual. So here we see that negative k d dx squared minus q dot is equal to 0. So if we were to move this to the other side, we would have this right here. And if we were to divide by k, it would be negative q divided by k. Okay, so we can see that q divided by k plus this is also equal to 0. So just a little visual so it doesn't look like anything came out of thin air. Sorry. So now to find the temperature distribution equation, we're going to integrate the heat conduction equation a couple times. So the first integration yields this right here. This can be plus, it can be minus, it really doesn't matter. Well, first we know that this is k, and we this right here kind of pointed out, so this whole thing was pointed out over here on how that's valid. So we divided by k. The x came from the integration, so plus this constant term. So here's our first integration. So now to integrate it a second time, we'll just show it here. So the second integration yields t plus qx squared, and you divide by that 2 times k, plus c1, this gets an x, plus a new constant term equal to 0. And if you simplify that down, this is equal to negative qx squared over 2k, your thermal conductivity, minus c1x minus c2. So now we'll consider the boundary conditions. So boundary conditions. And we know that thermal conductivity is equal to 2 watts per meter Kelvin, and heat generation is equal to 3 watts per meters cubed. So the first one here, negative k dt dx at x equal to 0 is equal to 5 watts per meter squared. And this can also be written as negative k c1 is equal to 5. So c1 is equal to 5 divided by negative 2. And we know that from this right here. So c1 is equal to negative 2.5. Okay. So we'll consider the second boundary condition. So the temperature at a length of 1 is equal to 20 degrees Celsius. And we'll use the temperature distribution equation that we saw for earlier here. So T is equal to negative Q x squared divided by 2k minus C1x plus, minus C2. So temperature here is equal to 20. Heat generation we know is equal to 3, negative 3. The length is at 1. 2 times the thermal conductivity of 2 minus the C1 that we just solved for, which is negative 2.5. And your x is equal to 1 minus C2. So if you simplify all of this down, you would get C2 equal to, we'll just, so this is negative 3, that's 4, and this would just, so this would just equal 23.25 negative. Because these terms would become, so all of this would become positive when you would move it over to the left-hand side, and it's ultimately negative because of the negative C2. So C2, C1. And now we would just plug it back into this equation up here. So T is equal to, we know that this is negative 3 x squared divided by 2 times 2 minus C1, which we know is, well, negative 2.5 x minus our C2, which we know to be negative 23.25. So this is ultimately Tx equal to negative 3x squared divided by 4 plus 2.5x plus 23.25. So that's the temperature distribution equation. If we were just going to do a rough sketch of that, we know that if x is equal to 0, then every term with x would cancel out, so that would just give you 23.25. So 23.25. And because the highest degree in this is squared, and that's a negative term, it would just look a little something like this. So that's a rough sketch of what the graph of this would look like. If we're considering when x is equal to 0, we'll just solve this equation for every x to be 0, which we kind of just did. So that's 0. That is also 0. So T at x is equal to 0 is equal to 23.25. And this would be degrees Celsius. We didn't really change that anywhere. So at t at x equal to 0 is 23.25. So that is how you solve this problem.